Greetings! Until now, we've been concentrating on pure substances. Now it's time to take the gloves off and start mixing all the chemicals in our chemical science kit together. We know mixtures come in one of two flavors: heterogeneous mixtures, which are mixtures that are not of uniform composition and have various locations that have different densities, and homogeneous mixtures, which have a uniform composition and a single density throughout. For the next few slides, we're going to focus on homogeneous gas and solution mixtures. And one of the goals in this set of lectures is to be able to define quantities that will give us the concentrations of each component in a mixture. Concentration measurements and units vary, so it can take some doing to keep it all straight. So keep some good notes. Before we get too involved in the nitty-gritty of quantifying components in mixtures, let's first look at some of the handy and experimental methods that have been developed to separate the different compounds in a mixture. The first method we'll look at is distillation. Now, in this process, the idea is to separate the components in a liquid mixture by exploiting the different boiling points of each of the components. In this method, we heat up the mixture until a component with the highest volatility boils and vaporizes. The component gas will make its way to the condenser where the temperature is decreased, usually with cooling water, recondensing the purified component and capturing it in the collection flask. Once we get this component, we can increase the temperature in the mixture and maybe boil off the next component. A similar process is shown in a cartoon of the typical industrial fractional distillation method used to separate the components in crude oil. Now, the solutions we collect are usually not perfectly pure, but much more so than they were, and there are a variety of distillation techniques that are used to increase the purity. Now, the second method we use can be given the general term crystallization and involves taking advantage of the various solubility properties of compounds in a mixture. The components are typically in a solvent mixture, and we try to create conditions that'll force one of the components to form a solid and crystallize. At that point, it's a simple matter just to filter the solution mixture and collect the solid. The typical ways to induce the components to crystallize out of the solution mixture is by cooling the mixture, evaporation of the solvent to reduce volume and change the overall concentration of the mixture, or by adding a second solvent to reduce the solubility of one of the components. Some exotic methods also include solvent layering, changing the anion or cation content of the solution, sublimation, and many others. Now, the third method is called chromatography. In this lab technique, the mixture is a liquid or gas fluid that is loaded onto the system along with an eluent or solvent called a mobile phase, which moves through a material called the stationary phase, which has a different level of affinity for the components within our mixture. The result is that the various compounds will travel through the stationary phase at different speeds, separating them. We then collect and identify the components at the other end of the stationary phase. The major factors that govern how well this separation technique works at separating components in the mixture are the solvents utilized, the concentrations of the components in the mixtures, the temperatures at which the experiments are conducted, and the polarity and ionic character of the components. All of these separation methods that we've talked about, coupled with the various spectroscopies we've talked about, give a chemist a huge array of tools in which to quantify the different components of a mixture and extract them from the concoction. Now let's get at the different ways we describe the concentrations of different components within a mixture. Now the first blend we'll look at is the gas phase mixture. These systems are usually homogeneous. Now, one way to characterize these gas mixtures is by using Dalton's law of partial pressures. Good to hear from our old friend Dalton once more. Now, he described the total pressure of a gas as the sum of partial pressures of each gas. For example, our atmosphere is primarily made up of nitrogen, oxygen, and argon gases. So let's assume these are the only components in the atmosphere. Dalton's law tells us that the total pressure in the atmosphere would be equal to the sum of the partial pressures of the nitrogen, oxygen, and argon gases. For dry air at sea level, the total pressure is about 1 atmosphere, and the partial pressures of the nitrogen would be about 0.78 atmospheres, for oxygen 0.21 atmospheres, and for argon about 0.01 atmospheres. Now, there are obviously trace amounts of many compounds, but these 3 are the primary components in the air. Other than partial pressures, one of the common methods to characterize the concentration of a certain component in a gas mixture is by its mole fraction. The mole fraction of, let's say, component I of a gas mixture would be to take the total moles of gas I in the mixture and divide by the total number of moles of the gas. Now, we know that our atmosphere is about 78% nitrogen, 21% oxygen, and 1% argon. These percentages divided by 100 are just another way of expressing the mole fractions of each gas. Now, we can set up 3 simple relationships for this mixture, assuming we have 1 mole of the gas mixture. Knowing these concentrations, we can calculate the amounts of each component if we were given a certain amount of the mixture gas. For example, if we had 22.4 moles of air given the mole fraction of each of the components in the air, we can use our relationships and calculate the moles of each component in that given amount of air. Now, we will get some round-off errors due to the lack of precision in the given mole fractions, but we have to obey the sig-fig rounding rules, okay? Now, this notion of a mole fraction leads us to a more general equation that we can use to calculate partial pressures. The following equation is the connection and works for ideal and real gas mixtures. Now, if we multiply the total pressure by the mole fraction of the chemical of interest, denoted by an I in the equation, we obtain partial pressures of component I in the gas mixture. So, if we multiply the total pressure of the atmosphere, 1 atmosphere, by the mole fractions of each component, we get the following. Now, the reason that the mole fractions and the partial pressures of the different components are the same values for air is that we assume that the total pressure was 1. So don't assume the mole fraction and partial pressures will be the same for every gas mixture. We kind of lucked out this time. They probably won't, just because the total pressure probably won't be 1. All right, that's enough for now. In the next lecture, though, we'll focus on liquid mixtures called solutions. See you there.